What would happen if a moon looked as if it were created rather than naturally formed? On the distant edge of the solar system, about 1.4 billion kilometers from Earth, Saturn's moon Mimas appears, at first glance, entirely ordinary. Yet the latest images from the Cassini spacecraft have left many observers stunned. Mimas's surface is dominated by the enormous Herschel crater, nearly 130 kilometers wide, forming a symmetry that feels almost unsettling. Data from the Cassini mission revealed that Mimas exhibits unusual gravitational librations. And even more astonishingly, deep beneath what seems to be a frozen, motionless shell, may lie a vast, moving ocean of liquid water. These new images are transforming this small moon into one of the greatest mysteries orbiting Saturn. This marks the beginning of a new journey, one that dives beneath the silent ice to uncover what is truly hidden inside one of the strangest worlds in the Saturnian system. For more than 2 centuries since its discovery in 1789 by William Herschel, a time when telescopes allowed humanity to see little more than faint points of light, but even as observational technology advanced dramatically, the original conclusions about Mimas remain largely unchanged. Mimas is a small moon, roughly 396 to 400 kilometers in diameter, far smaller than other prominent members of Saturn's system such as Enceladus or Titan. Spectral analysis and density measurements indicate that it is composed almost entirely of water ice, with very little rock at its core. Small, cold, and ice-rich from the beginning, Mimas appeared to possess all the traits of a primordial body, formed early and then left behind as the solar system evolved. But what truly shaped the scientific perception of Mimas was not just its size or composition, but its surface. When the Cassini spacecraft returned the first detailed images, scientists saw a world saturated with impact craters, overlapping like circles carved into ice over billions of years. There were no signs of flow, no global tectonic fractures, no erupting geysers, and no young ice resurfacing the terrain. Comparisons with Enceladus, a moon only slightly larger than Mimas, yet harboring a subsurface ocean and geysers erupting directly into space, made this conclusion even more convincing. If Enceladus was proof that a small world could be active, then Mimas was seen as its absolute opposite: small, cold, silent, and seemingly untouched by time. In thermal models, Mimas was assumed to have lost all of its internal heat very early. There was no strong radioactive decay, no significant tidal heating like that of Enceladus, and no mechanism capable of keeping its internal ice flexible. But as data became more precise, expanding beyond surface imagery to include rotational dynamics, thermal behavior, and interactions with the magnetosphere, these old assumptions began to be challenged. Because if Mimas were truly nothing more than a dead block of ice, then every aspect of its motion, from how it rotates and wobbles to how it responds to Saturn's gravity, would have to obey extremely strict limits. And it was precisely within those seemingly dry numbers that science began to realize that Mimas might not be as simple as it appears. To understand why Mimas unsettles human intuition so deeply, we must look directly at the Herschel crater, the scar that makes Mimas appear unnatural at first glance. A massive, sharply defined circle sits on a body that is otherwise almost a perfect sphere. Herschel is about 130 kilometers in diameter, nearly 1/3 of Mimas's entire diameter. Its walls rise roughly 5 kilometers high. Its depth reaches nearly 10 kilometers. And at its center stands a rebound peak rising about 6 kilometers. This is not a random depression. It is a complete, well-preserved impact structure, remarkably crisp and barely softened by time. A small body, like Mimas, with such weak surface gravity, should not have survived an impact of this magnitude. Models show that the energy required to form Herschel came dangerously close to the threshold for completely destroying the Moon. Just slightly more force, a higher impact velocity, or a more direct angle, and Mimas could have shattered into debris, becoming a short-lived ring of ice around Saturn. On larger worlds, large impact craters can be erased by tectonics, volcanism, or material flow. On smaller bodies, major impacts usually end the story altogether. Mimas sits uncomfortably between these two extremes, small enough that it should have been destroyed, yet somehow lucky enough to survive, carrying a scar far too large for its body. In many Cassini images, Herschel appears near the center of Mimas's visible disk. A nearly perfect circle, starkly contrasting with the surrounding terrain. It makes the entire Moon resemble a shell that has been deliberately punched through. Another detail that makes Herschel visually suspicious is how little it has deformed over billions of years. On icy bodies with internal heat, large craters typically undergo viscous relaxation. a slow, soft flow process in which high relief collapses, crater floors rise, and sharp features gradually blur. But the shock waves from Herschel did not stop at the surface. In impact physics, that energy travels through the entire body, reflecting and converging at the opposite point known as the antipode. This crater makes Mimas look unnatural, not because it defies physics, but because it exposes the limits of how we interpret a world through images alone. If the Herschel crater is the most visible mark of an ancient catastrophe on Mimas, then what it did beneath the surface is the most unsettling and the most important. When the object that formed Herschel struck Mimas, the energy released is estimated to have been equivalent to millions of megatons of TNT. Given Mimas's small size and weak gravity, the shock waves were not dissipated as they would be on larger bodies. Instead, they propagated through the entire moon, traveling at the speed of elastic waves in water ice, several kilometers per second, before converging at the point directly opposite the crater, known as the antipode. This is a phenomenon confirmed on many other worlds. From the Moon to Mars, where shock waves, after spreading across a spherical body, focus their energy on the opposite hemisphere, much like light being concentrated by a giant lens. On Mimas, with a diameter of only about 400 kilometers, this effect would have been especially intense. What Cassini observed on the opposite hemisphere was something more subtle. Fractured, chaotic terrain, and deep cracks known as chasmata. They are not as sharp or as visually striking as Herschel itself, but they extend for tens of kilometers, like fractures in a block of ice that was bent beyond its limits. For decades, Mimas was viewed as a solid, monolithic block of ice, a world with little meaningful internal history. But if its interior were truly rigid and uniform, the shock waves from Herschel should have produced far more obvious global deformation, perhaps even altering the Moon's overall shape. This led to an important hypothesis. Mimas's interior may have absorbed and dispersed the impact energy more efficiently than expected due to internal layering or the presence of mechanically weak zones. In planetary physics, layers with low viscosity, such as warm ice or even liquid water, can significantly dampen shock waves acting like a natural shock absorber. Even more intriguing, these fractured regions in chasmata show no clear signs of long-term surface activity. There are no flowing ice features and no obvious resurfacing processes at work. As impact models were combined with gravity data, rotational oscillations, and thermal measurements, the picture began to change. Herschel was no longer seen as an isolated scar, but as the starting point of a chain of hidden consequences, unfolding over hundreds of millions of years. If the geological scars suggest that Mimas once endured a violent physical shock in its past, according to all classical models, the surface temperature of a small icy moon with no atmosphere and no internal activity must follow a simple rule: a smooth decrease from the day side to the night side. This transition is normally controlled by the angle of incoming sunlight and the thermal conductivity of ice, with no sharp boundaries and no strange shapes. But when data from Cassini's infrared instruments were assembled into a global map, Mimas shattered those expectations. Instead of a gentle thermal gradient, a strangely familiar shape appeared. A large, sharply defined warm region resembling the Pac-Man character, with its mouth opening in a specific direction. Thermal inertia describes a material's ability to store heat and release it over time. Dense, compact materials with good thermal conductivity warm up slowly but also cool down slowly. In contrast, porous, fluffy material, like powdered snow, heats up quickly but loses heat just as fast once darkness falls. The Pac-Man map revealed that the two hemispheres of Mimas are mechanically very different, even though they look nearly identical in optical images. The Pac-Man region has significantly higher thermal inertia, meaning the ice there is harder, denser, and retains heat longer. The rest of the surface has low thermal inertia, indicating more porous, loosely packed ice, like frost that has been pulverized by countless small impacts. This boundary does not align with any major geological structure. It does not follow the Herschel crater, any particular latitude or longitude. Nor does it match simple illumination patterns. That rules out tectonic processes or internal activity as the cause. Instead, it points to an external influence tied to how Mimas interacts with its environment around Saturn. Some researchers once suggested that this sharp thermal boundary might be evidence of an internal heat source or some hidden subsurface activity. But if that were the case, why are there no other signs? No geysers, no active fractures, no young surface deformation. When we turn our attention to the energetic environment Mimas moves through, it is there that a subtle yet persistent physical mechanism begins to emerge, revealing how Mimas's surface has been gradually hardened along its direction of motion, producing the anomaly we call Pac-Man. To understand the Pac-Man thermal anomaly, science is forced to move away from the surface of Mimas and look into the space it travels through every second. Mimas is immersed in Saturn's vast magnetosphere, a high-energy environment continuously supplied with charged particles, especially high-energy electrons. Saturn's magnetosphere is one of the largest electromagnetic structures in the solar system. Charged particles are trapped and accelerated along magnetic field lines, forming streams of plasma wind that sweep across the inner moons. Mimas, with its close orbit and synchronous rotation, constantly plows headfirst into this flow of electrons. Crucially, Mimas always has a leading hemisphere in the direction of its orbital motion and a trailing hemisphere behind it. High-energy electrons, with energies ranging from tens to hundreds of keV, do not simply bounce off when they strike the icy surface. They penetrate the shallow ice layer, break molecular bonds, rearrange the crystal structure, and gradually make the surface denser and harder over time. In surface physics, this process is known as electron irradiation compaction, the densification caused by particle radiation. The key point is this: the mechanism has nothing to do with internal activity. There is no heat source from within, no exposed ocean, no upward flow of energy from the core. The Pac-Man thermal anomaly is a purely surface effect imprinted onto Mimas by the space environment surrounding Saturn. For years, this fact unsettled traditional models. Planetary science has long been accustomed to linking thermal anomalies with geological activity. On Enceladus, unusual heat comes with geysers. On Europa, it is tied to fractured ice and a subsurface ocean. But on Mimas, there is nothing this reality reveals that a world can appear completely inactive, yet still be profoundly shaped by its cosmic environment. Activity does not have to come from within. Sometimes, it comes from being placed in the wrong position within a vast energy system. When scientists analyzed the small rotational librations of Mimas using Cassini's precise tracking data, they recognized something impossible to ignore. The amplitude of the wobble was significantly larger than the limit expected for a rigid, uniform body. This could not be explained by electron radiation, nor could it be attributed to surface impacts. Its motion revealed that beneath the hardened shell, something was not rigid at all. What was once seen as evidence of a dead world, a silent surface, no geysers, no tectonics, now appears to be the perfect mask, concealing a deeper secret. The most subtle motion of Mimas as it orbits Saturn is invisible to the naked eye, but impossible for physics to ignore. Mimas rotates synchronously with Saturn. Much like the Moon, always shows the same face to Earth. In this state, a body never spins with perfect smoothness. Under the gravitational pull of its parent planet, it undergoes tiny rotational oscillations known as librations. For a completely solid object, the amplitude of this wobble can be calculated precisely, constrained by its moment of inertia and the overall rigidity of the body. By tracking Mimas's position with extraordinary precision over long periods, using orbital measurements, radio signals, and navigation imagery, scientists measured the Moon's rotational libration with unprecedented accuracy. The wobble of Mimas turned out to be roughly twice as large as the maximum value a solid, uniform block of ice could produce. It was a systematic, stable deviation, repeating consistently across many observation cycles. In rotational mechanics, an excessive libration means only one thing. The shell of Mimas is not rigidly locked to its interior. Mimas does not rotate as a single, unified body. This realization immediately shattered decades of assumptions. A moon long regarded as a geological fossil with no tectonics, no internal heat, and no activity, was behaving dynamically like a layered world. If the core and shell are not tightly coupled, then an intermediate layer with low viscosity must exist, capable of reducing friction and allowing the shell to slide. Solid ice? Too rigid? Warm ice? Still too stiff? A rock-ice mixture? Inconsistent with Mimas's density and size. Only one candidate satisfies all physical constraints: liquid water. This creates a profound paradox, a world with no surface signs of internal activity. No cracked ice, no geysers, no young deformation. appears to possess a dynamical structure similar to active ocean moons like Enceladus or Europa. The only difference is that Mimas hides it perfectly. Throughout the history of planetary exploration, humanity has learned to trust surfaces. Look for cracks, measure heat, search for eruptions. The Herschel impact once sent shock waves through the entire moon. Yet Mimas did not fall apart. All of this becomes coherent only when we accept that the shell is not the controlling element of the moon's dynamics. The rotational wobble of Mimas is an unintended confession by nature. It says that beneath a silent, symmetrical, and seemingly dead exterior, a system is still in motion. If the shell truly slides over a liquid layer, then Mimas is no longer just an icy moon scarred by impact. It becomes a candidate for a subsurface ocean in the most discreet way ever discovered. And this is the moment science must confront the next chapter, where hypothesis is no longer a choice but an unavoidable consequence of the data. A hidden ocean lying deep beneath the surface of Mimas. Structural models were rebuilt from the ground up based on mass, average density, and the measured rotational libration data. The results converge on the same configuration. An ice shell roughly 20 to 30 kilometers thick, beneath which lies a global ocean of salty water, surrounding a small rocky core at the center. Not a local pocket, but a continuous layer of liquid encircling the entire moon. What is astonishing is not the existence of liquid water. The solar system has gradually accustomed us to the idea of ocean worlds. What truly defies intuition is that this ocean leaves no visible trace on the surface. In planetary science, this is an almost unique case. Europa reveals vast fracture bands. Enceladus ejects geyser plumes hundreds of kilometers high. Titan hosts a complex methane-ethane cycle, while Mimas remains completely silent. With its small size, weak gravity, and cold outer shell, Mimas lacks the conditions needed to produce strong tectonic expressions. The outer ice layer may be rigid enough to fully isolate the ocean from the surface, turning the moon into a geologically closed system. This is precisely why scientists describe Mimas as a stealth ocean world, an ocean world that hides in plain sight. Thermal calculations indicate that if the ocean exists at a depth of around 25 kilometers, the pressure at the ice-water boundary would be roughly 30 to 40 megapascals, sufficient to keep water in a liquid state with the help of dissolved salts. The water temperature is estimated to be only a few degrees Celsius above freezing. Cold, dark, but stable, not an energetic environment like Enceladus, yet not a permanently frozen body either. The critical point is this: the ocean does not explain the surface. Rather, the surface distracts us from the ocean. For decades, the absence of thermal and tectonic signatures was used as evidence against any hypothesis of internal activity. Here, Mimas becomes a new prototype: small worlds with ancient, inactive-looking surfaces. No thermal expression, yet layered interiors and liquid water within. If this model is correct, the solar system may contain far more subsurface oceans than we once imagined, hidden beneath surfaces that appear long dead. Liquid water, even when cold, dark, and isolated, remains a central factor in questions about the potential for complex chemical processes. Mimas is not considered a prime candidate for life, but it demonstrates that the fundamental conditions for liquid water can arise in the most unexpected places. Because an ocean does not merely need to be detected, it must also be questioned in terms of its age and the energy source that sustains it. If Mimas truly hosts a global ocean, then the next decisive question is this: how long has that ocean existed, and what is keeping it from freezing solid? The best current models converge on a startling number. Only about 10–20 million years, most often cited around 15 million years. If Mimas's history were compressed into a single calendar year, its ocean would have appeared only in the final hours of December 31. A small world with an ancient, heavily cratered surface, one that should have cooled long ago, is instead carrying a remarkably young ocean within it. The evidence for this youth does not come from a direct measurement, but from what has not happened. The Herschel crater, despite its enormous size, has retained its sharp form. High walls, a deep basin, and a clearly defined central rebound peak. On moons with warm, ductile ice over long periods, such structures undergo viscous relaxation, where ice slowly flows crater walls collapse and the terrain becomes smoother. On Mimas, that process has not occurred. This suggests that the ice shell was warmed only recently, leaving insufficient time for large-scale resurfacing. This leads to the central question: where does the heat come from? Mimas is far too small to retain its primordial heat. Radioactive decay within its rocky core, if present at all, provides only a minor contribution. Far too little to sustain liquid water. There are no cryovolcanoes and no plumes, so what energy is quietly at work? The answer lies in orbital motion, a source of energy, not from within, but from gravity. Mimas orbits Saturn on a slightly elliptical path, with a semi-major axis of about 185,500 kilometers and an orbital period of roughly 22.6 hours. Its orbit is not perfectly circular, partly due to resonant interactions with other moons, especially Enceladus. As a result, during each orbit, Mimas is repeatedly stretched and compressed by Saturn's immense gravitational field. This process is known as tidal flexing. On Earth, tides raise the oceans by a few meters. On Mimas, tidal forces deform the entire moon by centimeters to meters. That may sound small, but repeated billions of times, this mechanical energy is converted into internal frictional heat. Thermomechanical models show that once even a thin ocean layer exists, tidal flexing can create a positive feedback loop. Liquid water reduces overall rigidity, greater deformation, more heat generation, continued maintenance of liquid water. Mimas does not need to be warm all the time. It may have remained dormant for billions of years, only to awaken recently due to subtle changes in its orbit. This makes Mimas a compelling example of geological activity that does not have to be continuous. Here, science is forced to confront a broader question. If an ocean can form within just a few tens of millions of years and potentially freeze again, how many worlds have undergone or are undergoing hidden cycles entirely beyond our ability to observe directly? Mimas shows that surface age does not equal interior age. An ancient shell can conceal a very young story beneath it. And a heat source does not need to be violent or obvious. It only needs to be persistent. The latest high-resolution images of Mimas have pushed far beyond the limits of conventional visual data. Becoming a direct challenge to the planetary geology models we once considered settled. The presence of geometric structures on its surface, precise to an almost extreme degree, combined with thermal anomalies that follow no natural pattern of solar illumination, has forced scientists to redefine the very nature of this moon. The contradiction between a silent, almost artificial-looking exterior and a set of complex internal physical responses has turned Mimas into a truly unique natural laboratory. And the story cannot end with Mimas, because Mimas may not be an exception, it may be a prototype. From here, we arrive at the final step. The greatest lesson a small, silent world can offer about how humanity understands the universe. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.